Good morning. I'm Allan Price, director of the John F. Kennedy Presidential Library and Museum, and with my colleague Stephen Rothstein of the John F. Kennedy Library Foundation, we welcome you and so excited to have you with us for this JFK Space Fest. Today's JFK Space Fest at the library honors President Kennedy's contributions to space exploration. President Kennedy challenged this nation to put a human being on the moon by the end of the 1960s and return them safely to Earth. Let's hear directly what he had to say about this.
There is no strife, no prejudice, no national conflict in outer space as yet. Its hazards are hostile to us all. Its conquest deserves the best of all mankind, and its opportunity for peaceful cooperation may never come again. But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills, because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win.
We now have a special greeting from NASA astronauts Nick Hague and Christina Koch aboard the International Space Station, who couldn't be with us here today, but wanted to send best wishes to everyone.
Good day. I'm NASA astronaut Nick Hague aboard the International Space Station with my NASA crewmate, Christina Koch. To everyone at the John F. Kennedy Presidential Library and Museum in Boston, we welcome you to our amazing orbital laboratory.
We're so glad we can join you today for this special commemoration of the 50th anniversary of the Apollo 11 landing of the lunar module Eagle, one of the greatest achievements in human history. We will never forget President Kennedy's words that inspired the nation to accomplish the goal of landing a human on the moon and to expand humanity's reach through the exploration of space.
As we honor President Kennedy's contribution to the U.S. space program and the historic significance of Apollo 11, we hope you will also enjoy learning more about our work at NASA. And perhaps one day, one of you will be part of the space program as well.
I'm now honored to introduce our first speaker today, Dr. Franklin Chang Díaz. He has served as chairman of Ad Astra Rocket Company, board and chief executive officer since July of 2005, formerly an astronaut with NASA for 25 years, and a veteran of 7 space shuttle flights. He holds a PhD in plasma physics from MIT and is the inventor of the Variable Specific Impulse Magnetoplasma Rocket Engine, the Vasimir engine. Dr. Chang Díaz is the author of Dream's Journey and To Mars and Beyond Fast. There will be a chance to ask Dr. Chang Díaz questions following his presentation. Please help me welcome Dr. Chang Díaz.
Thank you all for coming to this wonderful celebration of an event which really transformed many people's lives. And I wanted to point out to you that the words of President Kennedy more than 50 years ago resonated much beyond the borders of the United States. This was not just a U.S. Endeavor, but it was a world endeavor. And I was a young boy at the time, wanting to be an astronaut, and I wanted to join this in the United States. And so I wanted to walk you a little bit through that period of time, what it was like when Neil stepped down from the lunar module, stepped on the moon, and what happened since, and what do I think is going to happen in the next 50 years from now. So let me give you a little feel for where was I, and maybe think about where those of you who were alive, where were you at that moment when Neil stepped off the ladder. I had already arrived in the United States, and I was at the University of Connecticut. It was the summer, so I was just starting a little bit earlier than the regular course, because I had come to the US the year before, and I did not speak English. And I was just learning the language. I had come to the US because I wanted to be an astronaut, and convinced my father to send me give me a one-way ticket to the United States, and he did. He said, well, Franklin, listen, I cannot really afford to send you to the United States to study, but I will give you the plane ticket. And he gave me a one-way ticket. And he said, the reason I give you that is not just because I can't afford the return, it's because I know how hard this is going to be. And if you have the return ticket, you will be back. And I want you to have to work really hard. And if you do get into a lot of trouble, just write. And of course, we didn't have the internet in those days, and writing a letter would take a long time. It would take a long time to get there. It would take a long time for them to come back to me. And he figured that by then the crisis would have already abated. And so, but it was a good plan. So, and I have to tell you that if I had had that return ticket, I would have used it. I would have gone back because it was hard. So let me give you a feel. I had come the year before from Costa Rica. That's my home country. That's where I was born. And ever since Sputnik, I dreamed about becoming a space explorer. And, there were no astronauts in the Sputnik days, but shortly after that, the first astronauts were selected by NASA, and we also knew that there were cosmonauts being trained in the then Soviet Union. But there were only two countries in this game, only the Soviet Union and the United States. That was it. It was a chemistry of confrontation. And the rest of us were just sitting in the bleachers, watching this duel, I guess, or competition in the sky for supremacy between those two superpowers. And I just had to get into this game. And I had written a letter to NASA back in 1967 asking Dr. Von Braun, who was the head of the rocket program at NASA, how could I participate? Because I was going to graduate from high school in that year. And a few months later, I got this letter, which you can see it here. And of course, I couldn't read this letter because it's in English. And so I had it translated. But someone at NASA took the trouble to underline the last sentence in the second paragraph there. And the translator translated this letter to me. He said, careers at NASA were only available to US citizens. And I totally misunderstood the intent of the statement. I thought what he was trying to tell me was, come on over to the US and become a citizen, and then you'll get a job. And so, okay, I'm on. So I immigrated to the US back in '68 and started this journey. Of course, the space program, soon after the landing on the moon, President Nixon canceled the program, and my professors at the University of Connecticut said to me, Franklin, don't even think about going into space or space program because you'll never get a job. And that's because there were thousands of aerospace engineers out of work because the space program had been canceled. It was almost 5% of the national budget, and it went down to about a fraction of that in a matter of a couple of years. And so I'm glad I didn't listen to that advice. I went, however, to MIT and took a little detour into the field of plasma physics, because at the time, in the early 70s, there was an energy crisis in the United States and the whole world, and everybody was interested in energy. And nuclear power was a very up-and-coming technology, and particularly the promise of thermonuclear fusion. That is the promise of the hydrogen process that powers the sun. And so I did that. What happened? It's a technical problem. In Houston, we have a problem. So, yes, usually what happens is, okay, well, don't worry about it. We got to figure it out. Anyway, so I went to MIT and I started working in the fusion program, thinking that someday plasma physics and nuclear power would have an important role to play in space. That is, to power the rockets that would take us not to the moon only, but beyond, go to Mars and the deep planets, deep into the solar system. So time passed. The Apollo program was over. Skylab took place. We flew Skylab, and then the Apollo-Soyuz missions, also the one flight took place. It was sort of a lull. And all of a sudden, in 1977, the space shuttle came to life. And that is not in space, but it was flown from a big airplane, a 747, and they started doing the approach and landing tests where they would drop the space shuttle Enterprise from the 747, and it would just glide over the Edwards dry lake bed in the Mojave Desert, and they would land it and go for a touchdown to make sure that this thing could really fly in the atmosphere. So at that moment, NASA issued a call for another group of astronauts. Okay, another group of astronauts, and that was 1978. I applied, and the one requirement that I had not accomplished yet was that I was not yet a US citizen, but it was just in the process of doing that. That same day, same year, 1977, I took the oath of allegiance, and I became a proud American right here in Boston at the City Hall. And thank you. sent my application and was summarily rejected. So all that means to me is that you just have to try again. And so I sort of took my time. I was working at Draper Labs, and I was working on fusion power. And sure enough, a couple of years after that, lo and behold, another call from NASA requesting applications from American citizens for a new group of astronauts for the space shuttle program. And that was my call. I sent the application, which I had already in a file, just updated it a little bit, sent it over. And a couple of months later, I got called. I got a call to go for an interview. And I knew that once you get called from an interview, that means that you are withered down from thousands of applications down to the hundreds. And so it was like 3,500 applicants, and I was down to the group of 120. That sounded pretty interesting. So I went to NASA at the Johnson Space Center, went through all the application exams and evaluations, and in May of 1980, I was selected in the 9th group of astronauts. And you can see, I guess I'm the second, yeah, I don't even recognize myself. This is the second one. The second one in the bottom row from the left here. I'm right next to Charlie Bolden, who eventually also, he and I both got interviewed at the same time, and he became the administrator of NASA. I mean, who would know? Who would have known that? He was the administrator for several years, and Dan Burbank, who's going to speak next, is not in that group, but is coming later. So he's got a similar story. So anyway, fast forward, we, did a lot of stuff. 50 years from the Apollo program, the program matured. I better make sure that this thing works here. Yeah. We learned to fly this thing and to do a lot of really sophisticated work. Assembly of the International Space Station was a remarkable achievement. There were pieces that were manufactured in many different countries. They had never been fitted together on Earth. The first time they saw each other or one another was in space. And it all came together surprisingly fault-free. It was an incredible thing. And so we have become essentially a spacefaring species. And I just want to make sure this thing. So you can see here the space shuttle in relation to the International Space Station. The space shuttle is a big spacecraft, and the space station is even bigger. We're talking about something on the scale of a football field in size, and about 400 metric tons of hardware orbiting the Earth at 7.5 or 8 kilometers a second, going around every 90 minutes, with human beings living there. We have been living in space non-stop since the beginning of the century, since 1999. And so we are now poised for going beyond. This is also what has happened in the Earth. We used to have only a handful of satellites orbiting the Earth way back. Now we got about 500,000 of these things, and most of these things are dead. And there are more coming up. Now they're sending swarms of these satellites. Each one of these satellites is moving at velocities which are 7 or 8 kilometers a second. So we have a real problem of orbital debris and essentially overcrowding of the orbital space. So somebody's going to have to clean that up. And so these are the kinds of things that are coming down the line. So space has become really not just a place of exploration, but it has become a place of business. And this is really good. This is what makes the whole process be sustainable and be really, people have the profit motive, and now a lot of people get into it. The private sector gets into this. And now you can see, for example, the International Space Station right there at the bottom as a real anchor point. But there's other ideas of bringing private space stations. We're even talking about mining asteroids. You see up in the upper left, up there, asteroids that are full of precious minerals, water. Water is a very important consumable for space, and we intend to mine that for profit. The other thing is that many other countries are also involved in this game. So it is not just the US and Russia as it used to be, but now we have many nations, and it's a growing group of nations moving into space. So the problem that we are facing, though, is the transportation problem. And this is a problem that we've had for 50 years and even before, in that we have been relying on chemical rockets to do all of this work for us. And if you picture the Apollo Saturn V rocket, here it is broken in pieces here, you can see that most of that ship is fuel. Very little of what of the rocket itself is useful payload. And what actually got back to Earth was a little tiny capsule on the top. So the payload is very low. And that's just going to the moon, 250,000 miles away, pretty much in our backyard. And we want to be able to go throughout the entire neighborhood, to the whole of space. We want to be able to move through all of the solar system with human beings. Well, how do we do that? The propulsion systems we have today are not capable of doing that. We have to move to a paradigm shift in rocket propulsion and rocket transportation, so that we, which are only operating in the upper left here, low Earth orbit, cislunar, what we call cislunar, is all chemical propulsion. We now want to go beyond to Mars and beyond to the planets, to the outer planets and their moons. And then eventually someday we will embark on an interstellar flight. That requires completely different technology. So we are, in our company, and this is a project that I started at NASA, working on this sort of technology, and that's called the Vasimer. This is the engine that's in testing now in Houston. It is not a chemical rocket. It is an electric rocket. So we are moving to electric transportation in space as well as on Earth. A lot of people on Earth is moving to electricity. We're moving to electrical transportation also in space. And this is a rocket engine which, unlike the traditional electric rockets that we've had for many years, can process a huge amount of power. And that is what gives you the muscle to really go fast and efficiently in space. So how do you power electrically something in space? You have two choices. You either use solar power or you use nuclear power. Both of these are available. Clearly, near the Earth and the Moon, solar power is plentiful. But if you are going to go to Mars, or you're going to go to Jupiter or beyond, the sun is just going to be a bright star, not going to give you very much solar energy. You are going to be needing nuclear reactors. And that technology needs to be addressed. This is something that is that cannot be delayed any further. We should have started that 50 years ago, and we didn't. A lot of it is controversial because people worry about nuclear power, but without it, we will not survive in space. So it is a fundamental question that people are going to have to wrestle with. This is the Vasimer engine in schematic. You can see there on the upper right, a sort of a cartoon of how this engine, the rocket works. It's no longer a chemical mixture of chemical reactions there, but now we're talking about plasma. Now, plasma is nothing but a super hot gas, like the sun. When you heat a gas to temperatures like the sun, the atoms of these gas kind of break up a little bit and shed some of their electrical charges. And so you end up with a kind of like a alphabet soup of charged particles, negative and positive. You know, this is sort of a mixture of positive and negative particles, equal amounts of positive and negative, because if we have too much of many more of negatives, then the whole thing is negative. If you have too many positives, the whole thing is positive. So you got to have it all balanced out. So plasmas as a whole are neutral, but they are electrically conducting gases. Many of our lamps, plasma TVs, other devices that we use rely on this process. But the point here is that a plasma can be held very effectively inside a magnetic pipe. And a magnetic pipe has the advantage that it does not melt. So you don't have a limit to how hot you can make that plasma. And we make that plasma as hot as the sun. The plasma we are firing in our engine now is 5 million degrees. There's no material on the Earth or anywhere that we know that can sustain those temperatures. But we are able to control these kinds of temperatures in the laboratory now. So these rockets now have 10 times the performance of the best chemical rocket that we could ever build. And these are the rockets that will take us to Mars and beyond. This is an actual video of the Vasimer engine firing in Houston. Almost looks like a photograph, but it really isn't. It's a video. The engine is running here. You can see the plasma jet coming out of a magnetic enclosure, a magnetic nozzle. The plasma doesn't really touch the walls of the container. The only thing that touches the plasma is those sensors that you see passing back and forth. They're measuring the temperature, the speed, the performance of the jet, and they don't last very long. We keep them there only a few seconds, and then after a while they are not usable. Like you got to replace them. So this is how we measure the performance of these rockets. And so we're moving now to the deployment of this technology in various ways. First, because we are a private company, our investors say, well, you know, Franklin, Mars is not really a very good business now. There's nobody there, you know. You're not going to sell very many rockets to go to Mars. But there is a big market now in the vicinity of Earth and the Moon, and that is all of those satellites and all of that trash that I showed you has to be dealt with. And our business is essentially the trucking business, the logistics business, garbage collection, you name it. But you need a truck, and you need an engine on the truck to do that. So you can see here all of these potential areas of work. Eventually, as we mature and as we go back to the Moon, where we can test much more powerful engines of this type in the vacuum of the Moon, then we will develop there the engines that will take us to Mars. And that is what we'll do. This is a little bit of a history that you see here, what has happened over the years. So you can see that we have been developing this propulsion system for almost as long as the Apollo landing on the moon, for almost like 40 years, and we've been working on this. And it will be 50 years maybe before it's fully commercialized from the beginning. So now we're in this particular point. This is the first demo flight that we intend to do, probably in the year 2022, 2023. As just a simple robotic flight to test the engine and verify that its performance is the same as it would be, as it is in the laboratory. And then we intend to deploy trucks like this one here that you see, and these are solar-powered ships that will power those engines to deliver cargo to the NASA's Lunar Gateway, the mini space station that they want to put orbiting around the moon to start supplying permanent operations on the surface of the moon. They will need supplies, logistics, and we intend to provide that. And then eventually we go now to the real big dream that maybe some of the youngsters here will see, and maybe even they will get to fly. This is a ship that is as big as the International Space Station. It will be assembled on the Lagrange point near the moon. It will not be assembled near the Earth. It will be assembled near the moon. And it will be nuclear powered. It will have nuclear, you can see up on the upper right, the reactors. There will be 4 of these reactors, each one producing about maybe something like 10 megawatts of power, something similar to a submarine, to a nuclear submarine. The ship has got some interesting features that I wanted to point out to you, especially those tanks that you see in the central core. Those are fuel tanks, and the fuel is hydrogen. It will be carried as liquid hydrogen. And liquid hydrogen is an excellent shield against the radiation of space, which is one of the problems that astronauts will face in a journey to Mars and beyond, is the radiation bombardment from cosmic rays. So these hydrogen tanks are going to be wrapped around the core of the ship so that people will be living in the inner core, in the inside. That would be the living quarters. But inside those hydrogen tanks, you can see here a little blowout of that structure. Those slinky-looking things, they look like wraps of slinky-like structures around the core. Those are superconducting magnets. And these are very powerful superconducting magnets that will provide a magnetic shield in addition to the hydrogen shield. So you'll have 2 shields to totally protect the crew against the radiation of space. And that is the way we would go to Mars, and we will arrive there healthy and be able to work. These are some mission parameters for you to ponder on. We even have a departure date in case you want to make reservations. So it would be 20th of May and 2035. I don't know if I'll be able to see it, but maybe I will, and maybe I'll be even on it. Who knows? One-way trip, maybe. Anyway, no, this would be a return flight, definitely. And you can see here the parameters. Power 40 megawatts is about 600 metric tons of vehicle, very, very big. It will have a lander, which will land on Mars. And this is a sketch of the mission. And you can see from the various points, 1, 2, 3, 4, 5, 6, 7, they're described here. They're a little bit, there's a little jargon here, but I'll give you I'll give you a feel for number one. The first thing we do is we depart from the moon sphere of influence, which is in the Earth gravitational sphere of influence. So we spiral around until we peel off from the gravity of the Earth. That means we leave from the Earth sphere of influence to the transit to the Mars sphere of influence in item number 2. That takes 95 days, or 89 days. So the total so far from 1 to 2 to 3 is 95 days. When you get to the moon, you're coming in really fast because this is a very fast ship. You got to slow down, otherwise you miss Mars, and you don't want to do that. So you come in, and you separate. The lander will deploy big aerobraking bags, which will slow you down, land, but the mothership will continue on. And the mothership will arc around in item number 4, and it will take its time to come around and rejoin back on Mars on item 5, and we'll start slowing down and gradually lowering itself to about a 20,000 kilometer orbit around Mars. But by then, the crew has been on Mars for about 30 days. They are pretty much finished with their surface stay. Now they're ready to come back. They take off from Mars, dock with the mothership, and then on items 6 and 7, the ship then spirals out of Mars' sphere of influence and slings out to the Earth for another 90-day or 90-plus day journey. So this is the mission to Mars that we'd like to do. It's not the mission to Mars that is in the books right now, but this is the mission that we'd like to do, and we hope to convince NASA and maybe whoever wants to do this that this is the way to go. So this is the last image that I have for you, and it's a photograph taken by the Mars Curiosity rover from Mars, obviously, on a evening, clear evening sky. And that little tiny point of light is the Earth. That's where we all are. And the reason I close with that is because I figured that maybe someday, I don't know, amateur astronomer on Mars looking at the evening sky will take a picture of, look at that little point of light and tell, his or her son or daughter, hey, your great-grandfather came from there. So I'll stop right there. Thank you very much. Thank you. So I don't know, are we supposed to open for questions, or is it a little too late? Yeah?
Do we have some questions for Dr. Franklin Chang Díaz? Question over there.
What was it like in space?
Well, space is a wonderful experience, The most beautiful thing is just the sight of the planet, the sight of the Earth, which is round the way they tell you in school. It is truly round. There are some people who say that it's flat, but it isn't. It's round. So it's just I highly recommend it. So.
Question to the left.
Hi. As a teacher, what do you think we need to do for students to get ready to go to space?
Students to get ready to go to space.
Franklin, if you would like to ask a question, we've got some microphones here. So we're going to answer this one for the teacher, and then others can gather at the microphones in the aisles.
Yeah.
Great.
Students to get ready to go to space is study really hard. Mike Anderson, who died on the Columbia, he used to tell the students, you know, you're already training to be an astronaut. I mean, these little kids, you're already training for it. So you really got to pay attention and study hard. But the other thing I tell people is you got to be ready to fail. And you cannot be too worried about failure. I had a professor who used to tell me, Franklin, you know, if your experiment works perfectly, you've learned nothing. And he's right. To succeed, you have to fail. You have to learn to fail. And failure is part of the game. And just because, you know, this thing that they say about NASA, the failure is not an option, that was just a very specific case. But NASA is all about failure, excuse me, okay? So really, be ready to fail. Be okay with that. So, yeah.
What do you think of SpaceX?
What do you think of SpaceX?
SpaceX is great. I like SpaceX. I think SpaceX has really pushed the envelope and has really made people think about what's possible. There's some things that are a little bit, you know, maybe too much, but that's okay because you got to push the envelope. You gotta get out of your comfort zone. And I think SpaceX has pushed NASA and other agencies to get out of their comfort zone, and I think that's very good.
Thank you. This was really interesting. I have two questions. One is, if you could visit any moon or planet in our solar system, where would you go and why? And my second question is, if you think in our lifetime somehow it was not possible to have a round trip to Mars, would you support a one-way trip or only round trip?
Ooh. No, the one-way trip is not a good thing because, you know, on Mars, you know, you can't really breathe the air, and it's not very, you know, it's not so good. You know, it really not so good. I mean, it's not really fair to your loved ones, your families, and all the people that you leave behind. So, and I think there's no need for us to create a condition where you just have to go on one way. You got to be able to come back and tell the story. And we have the technology, and we can develop the technology to do that. So as far as the moons, I would go to Titan and Europa. Those are the most interesting ones so far that I've seen. And you know, on Titan, the atmosphere, you cannot breathe the atmosphere either, but the pressure is about right. So you don't need a pressure suit. You need a sweater, and you need to maybe put on a helmet. But and then Europa is probably hiding an ocean under the ice crust, and there may be life there. So I mean, it's really exciting, the stuff that's about to happen, and all these young people will see it. That's great.
On your planned mission to Mars, how many people do you want to bring, and what kind of experiments do you want to do on the surface?
How many people?
How many people do you want to take up to Mars, and what experiments do you want to do?
Yeah. Well, I'd say a crew of about maybe 4 or maybe 6, something on that scale. Probably not 12 or 20, and probably not 2. So experiments will probably be of many different types. A lot of physiological experiments, and also a lot of experiments to learn to live off the land. This is one of the most important things we have to do when we get to another planet, is to learn to use the resources there to be able to sustain ourselves. There's plenty of energy. We got plenty of power and energy to do things, but you know, gotta live off the land. You can't just bring everything in, you know, stored cans and frozen. So.
When you listen to the infrastructure by the Planetary Society, the Mars Society, billionaires like Musk and Bezos, they're looking at the typical 8-month out, stay for 50, 8-month back, which is costly and dangerous. Yeah. You seem to have a program that's going to work. Why haven't they embraced it? Is it political? Is it money? Is it time? What?
I think there is a rush, a desire to go. You know, I think people are a little frustrated because, you know, after all, it has taken us 50 years, and we could maybe have developed these technologies in the half a century that we've had. And so people are a little frustrated that we haven't really, you know, pushed forward to go to Mars. And so they want to go no matter what. And okay, well, that's okay. But I think that mission would be very fragile. It would be very likely that we lose the crew. If we lose a crew en route to Mars, it would be a horrible thing because we'll watch it for months and we won't be able to do anything about it. And it will set the program back by maybe another 50 years or more. So I just think that maybe it's time for us to do the homework that we need to do, get it done, and then do the mission that really has all the chances to survive. Give the astronauts a fighting chance. That's what I think. Okay.
Hi, my friend and I are engineers, so we have some technical questions about your spaceship, which looks really cool. Number one, why is do the superconducting magnets you have not interfere with any electronics? How does that work? And two, you talked about how hot your plasma gets. Why does that matter? Why does it matter that it's hot?
That's a great question. Okay, the superconducting magnets are very powerful. They have magnetic fields of the order of maybe 5 to 8 Tesla. This is maybe 2 or 3 times more than what you get in an MRI machine. When you get in an MRI machine in a hospital, you are getting inside a superconducting magnet. You probably don't realize that. Maybe it's not so good that you, yeah, it's safe, don't worry. But those magnets are operating at minus 268 degrees centigrade below zero. So it's liquid helium was circulating through those magnets, extremely cold. So these magnets that we are talking about are going to be operating at much higher temperatures. They're going to operate at the liquid hydrogen temperatures, which would be more like 25 degrees Kelvin, so much hotter than the liquid helium. They will use the liquid hydrogen, which we use as a propellant, to cool themselves. So this is kind of a double job. And they will shield the particles that are coming, are charged particles. So these particles are going to be bent. The trajectory is going to be bent by the magnetic field so that they do not penetrate into the crew habitat. As far as the rocket temperature, you know, the hotter the rocket exhaust is, the better the rocket. It's a pretty simple relationship in that a rocket's performance is very much related to the speed of the exhaust. The higher the speed of the exhaust, the better the rocket. And the higher the speed of the exhaust, the higher the temperature. The hotter that exhaust is, the higher the speed. And the reason is that, you know, in rockets, you have a choice. You either throw stuff out the back at a low speed, or a lot of stuff out the back at low speed, or a little bit of stuff at high speed. It's like if you're in a boat and you have a bunch of, you know, bowling balls, and you push yourself by throwing the bowling balls off the boat. You know, okay, you can do that, and the boat will move. You can throw the balls and you move. But you got to carry all those bowling balls on the boat, and they're heavy, so the boat is not going to move very much. Instead, what you can do is have a high-powered rifle and have the little bullets and fire that rifle, and you'll move the same. But you carry less bullets. So
Great. Just to let you know, we have time for 2, maybe 3 more questions.
Okay.
Yes.
So, you said you were, you said that you had gone on this, you had been on a space shuttle 7 times, And I was just wondering, what do you think you learned on those flights? Yeah.
Okay. Well, I'll tell you one thing that I learned in all the flights, because I flew so many times over many years, I was able to see changes in the Earth over many years. And one thing I saw, like the United States at night, was dark in the central part of the United States and very light, a lot of light in the eastern seaboard. But over time, the lights got more and more numerous as you moved west. So the population of the US has grown. The population of the planet has grown. I think one thing that I've learned is that this planet is coming quickly to the limits of the humanity that it can sustain. No matter how efficient we are, there come to be a moment when there's just too many. And we are doing nothing now more than ensuring our survival by learning to be a multi-planet species, that we can move out, that we can be in other places, and only not the Earth be the only place. So this is the kind of things that I've learned in seven flights space. Great question. Thank you.
Hello. You mentioned all the space debris that's been accumulating out there up to the moon and perhaps beyond.
Space debris. Yeah. Well, space debris is a growing problem. And
well, my question, if I could just finish. Yeah. My question, that debris is out there. What is the plan to dispose of it, assuming it's poisoned with radiation at this point?
No, there's not much debris that is radioactive. There are a few pieces way back from the Cold War that are nuclear based, but they are in very high orbits. They're safe. The debris that I'm talking about is much lower in what we call LEO, low Earth orbit. This is where all the little satellites are and all the satellites that give us our GPS and tell us where the next restaurant is or where all those satellites are there. The problem with the debris is that as soon as you have a collision, then you amplify this debris. You have a lot of fragments, and each one of those fragments is moving at hyper velocities. And there is a potential, if enough of these collisions occur, that you get to a point where that layer of orbital space becomes essentially unsuitable for life, or maybe unsuitable for any other satellite to live there, because you cannot get out of the way. There's just too many maneuvers to get out of the way, and it's just impossible to live there. It's just too much stuff. And that's called the Kessler syndrome, and it was predicted by an engineer at NASA a long time ago. It hasn't really happened, but it is one thing that we worry about. So we want to capture these pieces before they collide. There is no real regulation at this moment worldwide to reduce the debris in a coordinated way. So, but people are becoming more aware of it and learning to address it, and there's a lot of discussion going on this.
So are you going to bring it back home to Earth?
There are two choices. Some debris, you can bring it down to where it starts to skim the atmosphere and eventually slows down. It becomes a very pretty shooting star, and we think it's a shooting star, but it's not really. It's just a piece of junk that it's just it's okay. But okay, that's one way, and that's the less expensive way of getting rid of the debris. But it's not so great to be dumping it all on the Earth. The other way is to lift it up to higher and higher orbits and put them in graveyards. There are some ideas of having orbital graveyards where you just leave all this stuff and let it be polluted there. And there is yet another way, which requires a plasma engine, of course, that you will gather all this material and launch it on a trajectory to the sun and dump it into the sun. And that is a very nice ecological, processor, because that's where it all came from. So
We have time for one last question, if you can answer it
Yeah.
briefly.
Yeah, sure.
Yes.
What is your favorite part of a space flight?
What's your favorite part of space flight?
Favorite part is the launch. Well, I guess I have to say the launch is one of my favorites. Probably the nicest, most exciting one is walking outside. Opening the hatch and taking a spacewalk. That is a pretty impacting moment. So thank you so much for your questions. It's a pleasure. Thank you very much. You got it all